This is video number 4 of my playlist about the preparation of alkynes. In this video we'll have a look at the preparation of enynes and diynes by vinylation and alkynylation of terminal alkynes. These reactions often proceed under surprisingly mild conditions and can occur as side reactions when attempting to alkylate, arylate or acylate terminal alkynes. To suppress them, it may be helpful to check the conditions that are particularly favorable for these reactions. Let's first have a look at vinylations. Terminal alkynes can be dimerized to two types of product, a tail-tail or a head-tail homodimer. If two different alkynes are dimerized, product mixtures will usually result. Only if the two alkynes show significant reactivity differences, then a high-yielding heterodimerization might occur. Synthetically more versatile is the coupling of terminal alkynes with vinyl halides or with electron-deficient or otherwise reactive alkenes. Homodimerizations can be catalyzed by acids, bases and a number of transition metal catalysts. In this example, 20% of a pyridinium borohydride catalyzed the head-tail dimerization of cyclohexylacetylene. More common are transition metal catalyzed dimerizations, but unfortunately it is difficult to predict correctly if a head-tail or a tail-tail dimerization will occur. Here, just 2% of a palladium-carbene complex dimerized methyl-propagyl ether under essentially neutral conditions, mostly to the tail-tail dimer. Such homodimerizations can also succeed in the presence of strong bases, as in this example. With 3 equivalents of potassium terzbutoxide and 30% of iron trichloride, a complete dimerization of the starting alkyne occurred. In this example, small amounts of a strong base and an iron-carbene complex brought about an almost quantitative head-tail dimerization. The reaction was complete after 3 hours at room temperature. Propagyl alcohol, however, did not undergo this reaction. Propagylic alcohols show a peculiar reactivity and tend to oligomerize in other ways when treated with transition metal complexes. I'll show you some examples later when discussing side reactions. This is an example of palladium-catalyzed head-tail homodimerization under slightly acidic conditions, again at room temperature. Way more difficult than homodimerizations are heterodimerizations, that is, the coupling of two different alkynes. In principle, 4 products can be formed, and it is difficult to find high-yielding conditions and to predict the outcome correctly. In this example, a huge excess of propagyl alcohol was coupled with phenylacetylene. With the aid of 2% of a palladium catalyst, most of the phenylacetylene was coupled with the alcohol, while the oligomers resulting from propagyl alcohol were probably soluble in water or polar enough to be separable from the target product. Here, an excess of propagylamine was used, and a head-tail heterodimer resulted as main product. Thus, the predictability of these reactions is limited, and the correct identification of the products can also be difficult. Terminal alkynes can also be vinylated by addition to internal alkynes, as in this example. The propagylic alcohol reacted with high regioselectivity. Again, to improve the yield, a large excess of one of the two coupling partners had to be used, and large quantities of homodimers of the terminal alkyne were probably also formed. Here, a heterodimerization succeeded with only a slight excess of the terminal alkyne. The coupling was catalyzed by 5% of a cobalt complex and gave an excellent yield of enyne. Zinc was required to reduce cobalt-2 to the active catalyst. This is another example of heterodimerization of two terminal alkynes. Here both alkynes were hydrophobic and one of them was again used in a large excess. Catalysis by 5% of a ruthenium complex mainly yielded a cis-enyne. The outcome of such reactions depends on the precise structure and electronic properties of both alkynes. In this example, phenylacetylene yielded a mixture of hetero and homodimers, while 4-dimethylaminophenylacetylene mostly gave the heterodimer. Thus, this chemistry is not robust at all. Even small amounts of certain additives can have a huge impact on the outcome of these reactions. Here, depending on whether 5% of silver triflate or a sodium tetraaryl borate was added, a different product was formed. So much for the coupling of alkynes with alkynes. Let's move on to more predictable vinylations. This here is a typical coupling of a vinyl chloride with a terminal alkyne under Sonogashira type conditions. A copper acetylide reacted with a vinyl palladium intermediate under mild conditions to the expected enyne. For more variations of this theme, you may check part 3 of this playlist, where I discussed the arylation of terminal alkynes. Vinyl bromides are more reactive than chlorides and usually react much faster, but can also undergo elimination. Here, a vinyl bromide was coupled with 1 octine with the aid of 5% of a nickel complex and copper iodide. In this example, the vinylation was conducted in neat diethylamine, and the reaction was complete after only 1 hour at room temperature. Here, phenylacetylene was vinylated with a vinyl bromide and 3% of supported copper, without any palladium. A large excess of sodium hydroxide had also been added, but strong bases are usually not required for these reactions and can even cause eliminations or isomerizations. Thus, with the still more reactive cis-bromostyrene, no enyne but a diyne, the product of an oxidative alkyne dimerization, resulted. This could in part be prevented by using potassium carbonate instead of sodium hydroxide, but a product mixture still resulted. Palladium co-catalysis and a lower reaction temperature would probably give a better result in this case. Here, such a coupling proceeded with copper and palladium catalysis already at 0 degrees Celsius and with high stereoselectivity. Vinyl iodides are still more reactive than bromides and readily undergo all kinds of CC bond-forming reactions. In this example, a metallated terminal alkyne was generated from a vinyl chloride with LDA and then coupled to a vinyl iodide without any copper catalysis. Acyl chlorides and other activated carboxylic acid derivatives undergo decarbonylation with palladium or nickel 0 at high temperature. The resulting organopalladium or nickel intermediates can then be coupled with copper acetylides, as in this example. Here, the strategy was used to convert a synamic imide into an enyne. Let's now check some methods for the alkynylation of terminal alkynes. One of the most pervasive side reactions of terminal alkynes is the oxidative homodimerization, the so-called Glaser or Eglinton reaction. Traces of copper and oxygen will almost always bring about this dimerization, even at low temperature. Typical oxidants include copper-2, oxygen, and bromoketones or bromoacetates. Unfortunately, I could not find any example with hydrogen peroxide as oxidant, which is much safer and more convenient than oxygen. If a given terminal alkyne is to be coupled with another alkyne, a Cadiot-Chodkiewicz reaction is often the best choice. One of the two alkynes must first be halogenated, for instance by treatment with bromine in chilled aqueous sodium hydroxide, and can then be coupled with the other alkyne. Oxidative homodimerization of copper acetylides is related to the formation of cyanogen from cyanide and copper-2 and to the explosiveness of copper or silver acetylide. Unlike calcium or alkali cations, copper-1 or 2 readily oxidize acetylide anions to radicals by single electron abstraction. In fact, calculations have shown that copper-carbon bonds in acetylides already have some diradical character. Copper acetylides also form dimers or oligomers in which copper is bound both to the terminal carbon atom and to the pi bonds of another alkynyl unit, as sketched here. The distance between the terminal carbon atoms of the acetylides is short, just about 3 to 4 angstrom, what further facilitates CC bond formation upon oxidation. This here is a typical example of Glaser homodimerization. The oxidant in this case was copper-2. If a mixture of two different alkynes is treated with copper-2, as in this example, product mixtures usually result, unless the alkynes differ strongly in their properties. Here, the main product was the heterodimer, but a lot of homodimers were also formed. This example shows how problematic oxidations with air or pure oxygen can be. Because the starting alkyne is flammable and boils at 53 degrees Celsius, explosive gas mixtures are formed above the reaction mixture. This has caused a number of accidents on a laboratory scale and makes the scale-up of this oxidation all but impossible. One alternative to oxygen or stoichiometric copper-2 are bromoacetates. In this example, a terminal alkyne was dimerized under Sonogashira conditions by addition of a bit more than half an equivalent of ethyl bromoacetate as oxidant. Another alternative can be carbon dioxide, as in this example. Because carbon dioxide is only a weak oxidant, the dimerization required a high reaction temperature. With propagyllic alcohols or amines, however, a different type of product may also result. Thus, at a lower temperature, no oxidative dimerization occurred, but mostly a cyclic carbonate was formed by intramolecular nucleophilic addition to the alkyne. Sometimes oxidative dimerizations even succeed without any oxidant, as in this example. These were just standard Sonogashira conditions, and a complete homodimerization of propagyl alcohol occurred at room temperature. The reaction strongly depended on the structure of the starting alkyne, and no reaction occurred with propagyl acetate, for instance. If two different alkynes have to be coupled, it is often easier to just brominate one of them and then do a Cadiot-Chodkiewicz reaction, as in this example. Alkynes can be brominated by treatment with aqueous hypobromite, which is obtained when bromine is added to ice-cold aqueous sodium hydroxide. Here both a nickel and a copper catalyst were used, along with an excess of carbonate. This is another example of alkynylation with a 1-bromoalkyne. To prevent the formation of homodimers, one equivalent of sodium ascorbate was added. In this example, the required 1-bromoalkyne was generated from a vinylidene dibromide by heating with an excess of cesium carbonate. The terminal copper acetylide was also generated in situ by decarboxylation of a potassium propionate. Despite this complexity, a high yield of the target product resulted. Let's now check some potential side reactions. During transition metal catalyzed alkyne dimerizations, the starting alkyne may also trimerize or oligomerize. Here, for instance, mostly a trimer was obtained, not the expected enyne. This here is an example of the formation of a mixed trimer from two different starting alkynes. It is sometimes surprising that one main product can be isolated at all in view of the many possibilities, and the correct identification of products can also be difficult, as in this case. Conjugated enynes and diynes are highly reactive and on occasions even explosive, and many nucleophiles can add to these compounds. In this example, hydrogen chloride added twice to a diyne, mainly because of the large excess of copper chloride. Alkynes can dimerize in a number of other ways that do not yield new alkynes. Here, for instance, again a 1,4-dichlorobutadiene was formed by oxidation with air and gold chloride. Reducing agents like metallic zinc or alkali metals can reduce alkynes to olefins or cause reductive dimerization, as in this example. Propagyllic alcohols also tend to surprise us with unexpected transformations. Here, treatment of an electron-deficient propagyllic alcohol with triphenylphosphine gave a mixture of an allylic ether and an allyne. And with the aid of a cationic ruthenium catalyst, 2-methylbutanol dimerized at low temperature to a dienone. Oxygen in the presence of transition metal catalysts is a powerful oxidant and can cause many unexpected side reactions. Terminal or internal alkynes can, for instance, be cleaved to carboxylic acids, as in this example. Another potential side reaction during the oxidation of alkynes is their conversion into 1,2-diketones, as shown here. Thus, oxidative alkene dimerizations should be stopped as soon as the starting material is consumed to prevent further oxidation. Here are some further examples which you can also find in the description of this video. Under the Community tab of my channel, you will find a PDF version of the slides. The next video of this playlist is about the acylation, carboxylation and cyanation of terminal alkynes to yield acceptor-substituted electron-deficient alkynes. See you then.